Can you explain to the audience that what is the Swampland program, what is the motivation behind it, and how do you come up with the, what are called the Swampland conjectures? So if somebody wants to come up with a new Swampland conjecture, what kind of things that Swampland conjecture has to, satisfy in order to become a conjecture?
So the question is why do we expect that you can do something like Swampland, general principles? Well, in fact, the expectations you might get if you're a low energy effective field theorist are, a particle physicist, really. The naive expectation you might get is that there's really nothing much that gravity can say universally at low energies. And that's simply because, well, not only gravity is very weak, it's not so difficult to construct at the classical level. It's very easy to take your favorite quantum field theory, whichever you like, and couple it to gravity. There's for those people listening to us that have a bit more of a physics background, or if you don't, just go to Wikipedia, Einstein-Hilbert action, and look for coupling to matter. If you want to couple any matter to gravity, it's very easy. You just put square root of minus g in front and change derivatives to covariant derivatives. So classical level is very easy to do. Now, what we have been learning recently, and that's sort of like the core of the Swampland program, is that quantum mechanically, this is not the case. It's not so easy to do this. And why is that not the case? It has to do with general things, general properties that we would like to have in a consistent physical theory, like unitarity. So we would like our probabilities to always add up to 1. Doesn't make sense if you tell me you have a model for a coin flip where the coin has 50% chance of heads and 70% chance of tails. That makes no sense, right? If it's 50 heads, it's 50 tails. If it's 30 heads, it's 70 tails. That doesn't make sense. So that's an important principle. It's something as, it might sound stupid that is something that we would like to impose. And of course, we don't get anything new by thinking about probabilities adding up to 1 when we're flipping coins. But if we're thinking about more interesting processes, like things like black hole evaporation and the like, demanding unitarity, demanding that the evaporation takes like that, can give constraints. And a lot of Swampland arguments are based on, for instance, of expected properties of black hole evaporation. So for instance, one of perhaps the best established Swampland conjecture, which is this idea that there's no global symmetries in quantum gravity, has a lot of, heuristic arguments based on black hole evaporation. So behind it. So for instance, you could imagine that you have some global symmetry, a particle with a global charge, you throw into a black hole, then the black hole evaporates and the charge is gone. So that means that the charge is broken by quantum gravity. And that's something perhaps you would not have guessed from a field theory point of view. So that's one of the sort of like, these heuristic arguments based on black holes are perhaps why we think that maybe Swampland ideas are general and they apply to any quantum theory of gravity. But then of course we have more. We cannot prove them in general, cannot prove them in, because we don't have a framework to prove things in full generality in quantum gravity yet. But we can prove them in particular corners where we have more control. So for instance, one can give a proof there's no global symmetries in perturbative string theory. And there's arguments for it as well, very good arguments in my opinion, using holography, using the ADCFT correspondence. So these are 2 cases where you can prove them. And there's one more thing, one very important thing. You were asking, suppose I want to do a new Swampland conjecture, what do I need to do? Well, it's very nice if you have a black hole argument, but maybe that's hard in your case for whatever conjecture you have, so maybe you cannot do that. It's very, very nice if you have a proof. Of course, if you have a proof in this particular subset, it's very nice, but then people might still doubt maybe it's true here, but not true elsewhere, so on and so forth. But those things are acceptable not to have, it's like, as you were saying, it's like we are sort of still at early stages of learning what quantum gravity is at the non-perturbative regime. So there's many stuff that we could do. The one thing that you should always have, always have, and is the most important thing, is that whatever conjecture you have, it is supported by as many examples in string theory as possible. Why string theory? Well, there's perhaps other models for quantum gravity, but string theory is the only one so far which is so developed that you can ask quantitative precise questions. And string theory has about the low energy effective field theory, and string theory actually has a very large landscape of solutions. So there's one theory that gives you many different models of quantum gravity. If you have something like a Swampland conjecture, which you believe is a general property of gravity, it should be true in all of this. So you can use, and this is what most people in the Swampland program do, and it's one of the most important things, you should use string theory as a theoretical laboratory. Okay? So the most important thing, if you come up with a new Swampland conjecture, it's good to have the other two, but the most important thing is to say, well, okay, I have checked this property in 1,000 string theory examples, and it's always true. To me, that is a hint that you're doing something right, because it's very little chance that you made a conjecture and you checked in 1,000 examples and it's all true in all of those. Well, things can happen. It's not perfect. Maybe all the examples that you're looking at are somehow a bit similar in some way, but this is the thing that in some sense is the most convincing. So that's how you go about Swampland. On one hand, general arguments, general proofs when you can. And another very important, you try to check against the theoretical lab that is string theory.
So, correct me if I'm wrong, but if a particular low energy description can come from string theory, then it's not in the swampland, right? Then it's in the landscape.
Yeah,
Right?
that's the idea. So good. Sorry, I should have clarified that better. So string theory, we believe, is a consistent framework to obtaining quantum theories of gravity. So whatever you get from string theory, we believe is right. Okay? So you can use it to check.
Yeah,
If you
right.
get from string theory is good. If you get something that you think is in the swampland, it better be the case that you cannot get it from string theory.
But does it mean that if you have a swampland conjecture and then there is some, construction that comes from string theory, and for that particular construction, this conjecture doesn't hold, would you throw the construction away or would you throw the conjecture away?
Well, that depends, right? It depends on the detail and the precision and the degree of control that the construction has, right? So, for instance, if I have some conjecture about, I don't know, like size of couplings, and I base this conjecture on a string theory example where maybe I take the ingredients of string theory, I take the fields of string theory, the couplings of string theory, but I haven't properly solved the Einstein's equations, which are the equations of motion of string theory, because string theory contains GR. Well, then in that case, very clearly, I would throw away the counterexample, because it's a counterexample that is just not really a solution, right? Of course, in practice, in the cases where it's not so clear, it's much more subtle than something as stupid as I said. Just wanted to illustrate the basic idea. But yeah, if, for instance, let me give you a concrete example of the other. Suppose you come up with I don't know. Suppose you come up with the
Let me help you here. So there is one very famous. You can talk more about it, but there's a very famous swampland conjecture called the weak gravity conjecture, which means says that
yeah.
the gravity is the weakest force. And this is something that you have also worked on, where you showed that DGKT doesn't go well with weak gravity. So in that particular scenario, what would you do? Would you throw the weak gravity conjecture away, or would you throw away the DGKT construction away?
Very good. So what I was going to say is that, for instance, if you come up with any conjecture that it's not true, let's say in n equals 4 super Young Mills or in ADS factors as 5, which are completely well-established solutions with a lot of evidence behind of them, then you for sure throw away the conjecture. And the case you're talking about is something which is very, very interesting that we're thinking about right now. And the answer to that one is, I don't know. So just maybe perhaps to give a bit more context. So there is, as Hassan was saying, there's this one of the flagship Swampland conjectures, which is this weak gravity conjecture. Okay, tells you that in any consistent quantum theory of gravity, there has to be a particle whose charge to mass ratio, which is self-repulsive. Okay, so that its electromagnetic force is bigger than its gravitational force. That has a lot of evidence in string theory, and there's no string theory example, control or half under control, that challenges it. However, people have extended it to forces between, perhaps not just particles. Original formulation of gravity was about particles, but you can talk about forces between strings, forces between membranes. You could imagine like a membrane. And those ones, they are not in such a solid footing as the other ones. They are harder to check. but still they have been checked in many string theory examples, okay? In many string theory examples, they have been checked. And there's no black hole heuristic argument for them because the codimension of the membranes is very low. That's a technical point, but let's just know. And so in this project that you're mentioning that we had recently with Irene Valenzuela, what we were looking at was what happens to this conjecture. We were asking, is this weak gravity conjecture for membranes true in one particular scenario, which people have constructed in string theory, which is this called DGKT scenario. So this is a very interesting scenario because it's a vacuum, a string theory vacuum with negative cosmological constant, where the size of the extra dimensions is tiny compared to the cosmological constant. So that is the only example that we have like that. And that makes it very interesting because, we don't see more than 4 dimensions in our own universe. So that vacuum is a lot more like our own universe than any other vacuum that people have studied in string theory with a negative cosmological constant. And it's very well controlled, but subtleties remain. So there's ongoing debates. I don't think the details are that important, but people are still debating whether this thing really exists, really works or not in string theory. And so what we wanted to, the idea that we had was like, well, okay, let's see what happens with when we try to check this with gravity for membranes, which is not super well established in this DGKT scenario, which is also well established, but it's not super well established. And what we found, as you were hinting at, is that the weak gravity conjecture doesn't hold in this scenario. So you are completely right. You either have to throw away the weak gravity for membranes, or you throw away the scenario. Now, let me tell you, this is a project which is absolutely great to give talks about because everybody's happy. Whoever likes the weak gravity conjecture tells you, oh, very good, the scenario doesn't work anymore, the DGKT scenario. And whoever likes the DGKT scenario tells you, oh, very good, you have proven the weak gravity conjecture doesn't hold. But the reality is we have done neither. We don't know. So we are actually now working to check weak gravity conjecture in scenarios similar to this DGKT, but which are under better control. They don't have this scale separation thingy, which makes DGKT very interesting, but in exchange, they're much better in control. So to answer your question, finally, I just don't know yet. I don't know which one I have to throw away. Do I have to throw away weak gravity or DGKT? But I know I have to throw away one of them, and either possibility is very, very interesting.
So if you like this video, give it a thumbs up and consider subscribing, and the YouTube algorithm thinks that you will also like this video.